So in college, I had to learn about all the elements on the periodic table, and most were pretty fascinating, but it just got to this one that put me to sleep. It was brutal. Yeah, I'm talking about borium. Welcome, welcome, welcome. Today we're going to talk about engineering materials in our next generation chemistry lesson. First thing I'd like to talk about is material scientists. These guys analyze the chemical properties and structures of different man-made and natural materials. Things like glass, rubber, ceramics, alloys, polymers, metals. What they do is they study them to learn and gain new knowledge. They take this knowledge to devise ways to strengthen existing materials, combine different materials together, and engineers then select from these materials on what would be the best choice to make the design that they need. In the engineering design, when they're doing this, when engineers are deciding which materials to pick, they're going to use this model here, the engineering design model. First, they have to define, delimit the problem. Then they design and test solutions. They optimize the design and the solutions. And then finally, they implement and communicate their results. And I'm going to go into this in better detail. But first, I want to give you a little background. I want to give a little scenario on using this here. And here's our scenario. We're going to collect water from fog. In some areas, it is common to see fog even though rain is rare and water is scarce. Engineers are developing ways to efficiently harvest water from the fog using engineered materials that collect water from air. So having said that, we're going to talk about harvesting the water from the air. Let's define and delimit the problem. Let's talk about this step here. How much water is needed in the area? So this is what we mean by defining the problem. How much water is needed? Would the fog be enough to supply the water year-round? So is there enough fog to meet the needs of year-round needs annually for this area? What plants and animals depend on the fog water to survive in the area? Will reducing the amount of water in the air harm these organisms? So you got to think about when we're going to harvest something, how will that change other systems? Reducing water in the air decreases humidity. So if we take the water out of the fog, that's going to decrease the humidity. And what unintended consequences could happen? All of these things need to be considered. So we're defining and we're delimiting the problem. So we can maybe go in circles here as we're trying to figure out if this is a viable option for our area. Now we're going to design and test solutions. But how do you come up with the design? Sometimes knowledge leads to inspiration. For instance, the Namib Desert is a very, very dry area. It has very, very little moisture, but there is a fog that rolls in a couple times a week because it's close to the coast. There's a strange little beetle there that's evolved to survive in this dry area, and it's called the Namib black desert beetle, or species name Stenocara. And what the Stenocara does is it will bend itself towards the fog in a 45-degree angle. And it's got a very interesting shell. On its shell there's bumps, and on the bumps it's got different regions. It's got polar regions, or hydrophilic means water loving, which is polar molecules, and these polar molecules are located at the tops of these bumps on the back of the beetle. And then the valleys, the rest of the shell is very hydrophobic. It's nonpolar. And so what happens as the moisture comes, it does not collect in the valleys, it collects on these ridges. And as it collects, it gets bigger and bigger and bigger until it gets too big, and then it falls off the ridge into the hydrophobic area that does not attract water. So it quickly rolls off this area. And because it's arched up, it rolls off into the face where this beetle cleverly is able to drink water in an area where water is extremely scarce. So we're starting to use this technology of hydrophobic and hydrophilic areas in on nets, and these nets will collect water. They'll beat up and they'll drip down. And this is actually a picture in California where they're using the nets to collect fog water off the coast in California. The next thing we got to do is optimize design solutions. So let's select the right solution. So we know we're going to make this net. Now we're trying to figure out which material to choose from to make the net out of. And so what engineers can do is create a design matrix for fog collecting material. To figure out which material we're going to do, let's figure out what criteria the material needs to do. What's important that this material can do? And so in this example here, we're going to say durability. We don't want these nets to fall apart quickly. That's a criteria. Water collected. How good are they at collecting the water? Some materials will collect water better than others. Here's another criteria. The cost. How expensive it is to produce these nets. And perhaps our last criteria in this example is going to be algae resistance, because if it's collecting water and their sun is out, it will also start to collect algae. It'll start collecting algae on the surface, and then it won't collect water very well. So you're going to have to clean these nets regularly to get rid of that algae. So algae resistance could be another criteria. But these criteria, some might be more important than others. So what they do is they weight them. And in this case here, durability is weighted the heaviest, and then water collected, and then the cost, and the least important thing for these engineers was the algae resistance, and the most important was durability. Now we've got 3 materials to choose from, and we take a look at these materials and we have values for them: durability, water, cost. So we analyze these materials and we create values for them. In material 2, we've got these values. So 5 being they score very well, and 1 meaning they score very low in that idea. So we're going to take a look at these ones here. For instance, the durability in material 1 is the best, material 2 is the worst durable, and 3 is it's not bad. Okay, now how do we know which one to pick? Well, we're going to add up all these scores. We're going to total them up here. Now we don't just add 5 plus 2 plus 1 plus 1. These are weighted. Durability is the most important. So since we gave durability a factor of a value of 4, it's weighted as 4, and this one here scores very high, it scores a 5, we would actually score that as a 20. So this is 20. We say 4 times 5 is 20. Water collected, we do 3 times 2, weighted 3 times 2 is 6. The cost, 2 times 1, that's a value of 2. And algae resistance, 1 times 1 is a value of 1. We add up all the values and I come up with this number 29. So remember, when you do the total points, it's weighted. So you have to multiply whatever these columns are by the weighted value. So in this one here, we do 4 times 1. This will be a 4. And 3 times 3 is 9. 2 times 2 is 4. 1 times 4 is 4. So we have a weighted value of 21. And the last one here, we've got 4 times 4 is 16. 3 times 4 is 12. 2 times 1 is 2. 1 times 0, look, there's no algae resistance on this one, is 0. And that adds up to 30, which would mean that the actual best choice when we analyze this is actually material 3. Even though it has no algae resistance, the durability, the water collected are really the most important things to us. And so weighted value, we would select material 3. This helps to consider trade-offs and cost benefits when you have to decide which choice to make. And that is a decision matrix. Implementation and communicate the results. Implementation is often not the final decision of the engineers. There are other factors that come into play when determining if these ideas will be actually implemented. So we made these nets, will they actually be put on the beach to collect the fog? So there's considerations to be determined, things like businesses. So the businesses might determine if they're going to buy this net from you or not. It's not the engineer's choice to put on the beach. It may be the business economics of the situation. Is it worthwhile for a business to collect that fog versus the cost of what's being put there? So economics. Another thing is politics. The policies that we have in place will determine if we put these engineering ideas in motion. You might say, well, politics, we need more water collected, so that would be something they do. But then the politics might also be, well, we're protecting the land there, and you put all these nets all over the place, and that's kind of disturbing that ecosystem. And you're also going to have engineers coming over there, or maintenance people coming over there and cleaning the algae off them and doing the maintenance like that a lot. So politics can play a role if things get pulled into actual use. Culture, what are the values of the people where this is going to be established? The culture might be very, very don't harm our nature kind of a culture, or the culture might be more of a we need to produce more materials kind of a culture. So the culture will play a role in if this gets implemented or not. It's not just the engineer's choice. The life cycle of materials. So when materials are developed, they go through a process, and we're going to talk about the life cycle of a cell phone in this picture here. So the first thing that's going to happen is we have to obtain the resources. The resources will have to be, when there's metals and stuff like that, expensive things like batteries and things, they have to be mined and drilled and obtained. The next thing to do is those materials go to production, and they'll go to factories where they get refined and put together in use, and we'll build the cell phone here. Next is distribution. Now we have to deliver the phones all around the world to the consumers that want the phones. The consumer gets it, and we use our phones for the life of the phone, and then eventually we decide we don't want the phone anymore, which finally leads to disposal. At that point, you might sell your phone or trade it to someone else, give it to somebody else. You might recycle the phone where it's allowed to go back into production, or you might just dispose of the phone and get rid of it altogether. So this is the life cycle of a phone example, but we can have life cycles for anything. Obviously all materials, all products. If we look at these different engineering criteria, we've got some different criteria such as reducing the energy consumption of an appliance. So we got these different things that are important. And we take a look at the life cycle of a product, and this is for a cell phone, but it could be for anything. Everything has to go through these 5 different stages. What I want you to do is pause the video and see if you can figure out these criteria, which life cycle stage does this criteria fit into. And I'll give you a hint. There are 5 criteria, and there's 1, 2, 3, 4, and right here 5 different stages. So pause the video, see if you can figure out which goes where, see if you understand what we're talking about. Okay, hopefully you did that. Now let's take a look at some different engineering materials. We're going to start with metals. Metals have low electronegativity, but before I get into that, where are the metals on the periodic table? We have this stair-step line, and to the left of the stair-step line are the metals. So all of these elements over here are the metals, and to the right are the non-metals. Now, they have low electronegativity because if you guys remember, electronegativity is lowest, the least electronegative elements are at the bottom and the left side. These are the elements that have the largest atomic radius, which means the electrons, that's a very big electron cloud. If it's a big electron cloud, it does not have a good ability to add electrons to it. That's what electronegativity means, the ability to add electrons. So because it's a big cloud of electrons around the nucleus, it's harder to add electrons to it. The highest electronegativity is the top right, stopping at fluorine. Remember, the noble gases are not electronegative. And that's because they are much smaller and they're able to grab electrons from neighboring atoms a lot easier. So they have low electronegativity. A lot of students make a mistake and they think it's high on a test. Why? Because they associate metals with electricity, and so they think it's high. But pay attention. Electronegativity is something we learned about in chemistry, and metals have low electronegativity. Metals are cations surrounded by a sea of electrons. So they're cations and their valence electrons are free to move around. And this moving around allows metals to these electrons allows metals to conduct electricity. It allows metals to change their shape without breaking, so they're not brittle, because these electrons hold it together. Even if the cations, the nuclei, kind of shift, the electrons hold the whole thing together like glue. So what are metals ideal for when we talk about engineering? Well, they're great for structural support because they're very strong and they're hard. They're good for fastening and holding materials together like nails and screws and tacks. They're great at conducting electricity because of those that sea of electrons. They're free. The electrons are free to move about, so you can conduct electricity. Metals are smooth and easy to clean. So if you want a surface that's smooth and easy to clean, a metal's a great choice for that. Metals are very resistant to high temperatures. So if you're going to do something that the temperatures are going to increase very high, metals are a good option for that. And they are antimicrobial, meaning that pathogens, viruses and bacteria they don't exist very well on metals. So these are great choices for dental, medical equipment, and when you're going to put artificial joints or artificial attachments into people, you would want something that's antimicrobial. Our next engineering material is ceramics. Ceramics are made of ionic or covalent bonds. They have electrons that are transferred or shared between atoms. Remember, in ionic compounds, an electron is given from one ion to the other. The cation donates to the anion. So that's what I mean about transferred. Or it could be covalent. Ceramics can be covalent bonds as well, where we have a sharing of electrons. And hopefully you guys remember that sharing of electrons is the strongest of the bonds. They form rigid atomic structures. So here's an example of a ceramic magnesium oxide where we have magnesiums surrounded by oxygens, and it creates a very rigid structure. Because of this, ceramics are hard. They're heat resistant because they don't have those electrons that are free to move. They're poor conductors of electricity, again, because they don't have those valence electrons that are free to move. They're all bound up in donated electrons or shared electrons. And they're brittle, meaning if you put force on a ceramic, it's not going to change shape, it's going to break. So that makes ceramics ideal for things like pottery, bricks, cement, glass. Yes, glass is a ceramic. Electrical insulators. So you can see wires with ceramics surrounding it because they are poor conductors of electricity. Heat-resistant tiles. Spaceships have ceramics plating the outside because they're so heat-resistant that it protects the spaceship. If damage happens out in space, it gets collided with something and ceramic tiles are damaged, the astronauts have to go outside and repair them before they come back into our atmosphere, because the thermosphere is so hot and the friction of our atmosphere as the spaceships come back in, it would destroy the spaceship. So we need some very heat resistant materials to protect the spaceship and the people inside. Engineering materials, semiconductors. Let's talk about the semiconductors. Semiconductors are poor conductors of electricity at low temperatures, but start to conduct electricity as the temperature increases. They consist of metalloid elements, and these metalloid elements are located on the stair-step line. Remember, to the left are the metals, to the right are the nonmetals, and on the line itself we have the metalloids. So we've got boron, silicon, germanium, arsenic, antimony, tellurium, and polonium. So here are our metalloids on the stair-step line. The electrical properties of semiconducting elements such as silicon change when impurities are added to the crystal in the process called doping. So let's talk about doping right now with semiconductors. Silicon has 4 valence electrons, and you should know this by now. Look at your periodic table where it's located. It's in column 14, group 14, and group 14 has 4 valence electrons. So what happens is when silicon is around other silicon, remember the ideal state of valence electrons around elements is 8. So silicon will bond with 4, so one silicon will bond with 4 other silicons around it, and so forth. Every silicon has 4 around it. Every silicon's got 4 around it, and it's all locked up like this. All the valence electrons are completely covalently bonded, keeping them immobile. These electrons are not free to move in this position. Let's try to dope this crystal with phosphorus. If we take phosphorus, we're going to dope it. The first thing we have to do is remove a silicon from the crystal. So we have an empty spot here, and we're going to replace that spot with phosphorus. Phosphorus has 5 valence electrons. Notice on your periodic table it's in group 15. It's got 5 valence electrons, and so it's going to bond with the silicons, but there's 1 extra electron, and this extra electron allows for the conductivity of electricity. Because of this extra electron here, that electron is free to move, and if it's free to move, it can conduct electricity. We can also dope with other impurities like boron. The difference between boron and phosphorus is phosphorus has 5 valence electrons, but boron has 3 valence electrons. So when you dope with boron, you have one situation here where there is missing an electron, and this we call a hole, kind of like a positive charge. There's a missing spot right here. And what can happen with boron is with this missing spot, electrons from other areas can replace that spot, and so the hole is free to move. And as basically what's not really moving as the hole is the electrons are free to move around because there's a hole. So doping with boron creates a hole. The hole can act like a mobile positive charge because it can swap with neighboring electrons and move around the crystal. So if we have boron doped, we can have electrons move because there's a gap, and because there's a gap, the electrons can move. The next engineering material we're going to talk about are polymers. Polymers are chains of hydrocarbons, and as the name implies, this is a molecule that's made up of hydrogen and carbon. So hydrocarbons can be various in size. The smallest hydrocarbon is just 1 carbon surrounded by hydrogens, that's methane, but we can add more and more and more carbons. Be creative, it can be as big as you like. And we've got 3 different models here of hydrocarbons. We got the Lewis model, which you guys are familiar with, drawing those Lewis dot structures. We have a ball and stick model, which is something you can actually build with model kits. And this shows the angles better because when you draw it like this, it looks like these are 90-degree angles, but the reality is these angles are 109.5-degree angles when you have a tetrahedral. You have 4 things connected to a carbon. And then finally we have a space fill model. Space fill models are probably the most accurate of the models because when there's a bond, there's not this big open chain of electrons going back and forth. They're being shared, and this kind of these atoms, these electron clouds I should say, are kind of mashed together. So this is the more accurate one, and this is showing the proper angles, but more what the atom would, or the molecule would look like. Polymers can be linear, branched, cross-linked, or networked. In a linear polymer, it's just a chain of carbons, and the hydrogens are not illustrated here. The black little circles are the carbons. And it's just long chains, and these chains are associated with each other. They attract towards each other with intermolecular force. Nylon is an example of a linear polymer. Nylon has high density and high melting point. It's made from long polymer chains that are stacked very closely together. Because of these long chains, there's not much interfering. You can lay them on each other and you can get really, really dense. And this will make sense when I talk about the next one, branched. And an example of nylon is, well, nylons. Let's talk about the branched structure. When you have a branched polymer, you've got the carbons, but there can be branches. It's not just a single line, it's got branches in there. And so what happens in this is it can't stack as well because the branches are in the way. Imagine taking sticks and just stacking them up together. You can get it pretty dense, but if you have sticks that have branches off on the sticks, you're not going to be able to stack them together as well. And so an example of branch polymers are low density polyethylene, or LDPE. You might see this on labels on plastics and stuff like that. These polymers are flexible and have many subunits and side chains. So it makes it less dense and it makes the plastic flexible. And you might relate to this with your plastic bottles, probably have an LDPE stamp on it somewhere. And these are, again, flexible. A cross-linked polymer is chains that are actually connected to each other. So we've got these chains and they're connected to each other like this. An example of cross-linked polymers is synthetic rubber. Synthetic rubber is very strong. This polymer forms long chains with strong covalent bonds. So these covalent bonds are much, much stronger than just stacking them up and having the intermolecular forces putting these things together. So synthetic rubbers are really strong, and we use synthetic rubbers in things like car tires. The last form of polymer is a networked polymer. In networked polymers, you don't really have much of a chain. It's like they're connecting to each other constantly, and it makes a long, huge web. And because of this, they're extremely strong because these are all covalent bonds. Epoxy adhesives are examples of networked polymers. They're very strong and heat resistant. These polymers may have connections between the chains. An entire sample could be one molecule. So the whole thing here is one molecule because it's not having intermolecular forces with another molecule. So it's extremely strong. So we have epoxy adhesives that come in two different tubes. So the chemical reaction will start when they come in contact with each other. And you can make a very, very strong adhesive, and but you've got to keep it apart, otherwise it'll just turn this strong adhesive in the tubes. You can see epoxies on floors. It's a nice, strong, clear finish to a floor. Basketball courts often have this on them as well. So let's talk about some factors with polymers, some situations here about the different types of polymers and what sets them apart from each other if we want to pick the right material for our engineering task. The greater the attractive forces are between molecules in a thermoplastic, the tougher the material will be. So what this is saying is the stronger the attractive forces, the more those chains are attracted to each other, the tougher the material will be. The greater intermolecular forces between the chains also means the plastic will melt at a higher temperature. So if you have strong intermolecular forces, it's going to take more heat before you can break that apart, before it will melt. So here's an example here of two plastics. One is being held together and they're kind of like in an oven, and the other one is melting. The bottle with the stronger intermolecular forces, so the ones that are connected to each other stronger, is most likely to be intact bottle. So by looking at this picture, this one here is probably the bottle that has stronger intermolecular forces. The bottle that would be easier to recycle is most likely the melted bottle. So if it's weak, it breaks down easier, which makes it easier to recycle. And this is that dilemma that a lot of people that don't really understand chemistry and science very well come up with. If you want it strong, it's going to be strong all the time. It's going to be harder to melt. It's going to be strong. It's going to be dependable. But if you're looking for something recyclable, that's probably not your best option. If you want it to be recyclable, you're going to have something that's not going to be as strong, not going to be as dependable. So there's those trade-offs. What's the criteria and the trade-offs that are most important to the situation we're building things from is what we consider. Next one we're going to talk about is composites. And engineering materials that are composites are different materials combined to form a new material with unique properties. Typically, a composite is made up of one component surrounded by another component. Fiberglass is an example of a composite. Glass itself is strong, but it's brittle. In fiberglass, what they do is they take glass fibers, so shredded glass fibers, and then they cover it in a plastic. And this produces a light, strong, flexible material. Wood laminate is a composite. Wood laminate are like some floors you buy and you snap them together. And these are wood laminate floors here, and it has different layers. The laminate floors are composed with a clear protective layer. So they put some clear film on it. And then the next thing we do is we have a wood pattern. So it's a very thin sheet of wood underneath it. And then you have a stronger, maybe not as pretty wood to look at. So the floors look nice, but it's not this big expensive piece of wood. And by doing that, you got a nice strong floor. And also maybe the wood that you like wouldn't be very strong for a floor. So you can get that pretty look and get a strong base for it as well, and then you protect it with something nice and clear. When you're adding multiple pieces together, that's what a composite is. Waterproofing your clothes is an example of a composite. So adding a layer of hydrophobic spray, hydrophobic means water fearing, spray to your clothes turns the clothes into a composite. So if you spray your clothes with this, now it's not just cloth, it's cloth with this protective hydrophobic spray on there. So you have something new. It's got unique properties. It's cloth, but it's waterproof. Before I get into the next one, I need to talk about some terms I'm going to be referring to. And the first term I'm going to talk about is plasticity. This is the ability to change the shape permanently without breaking when force is applied to it. So something has a plastic property, that means it will change its shape when you add force to it and it won't break. So it's the opposite. Plasticity is the opposite of brittle. Another term is elasticity. This is the ability to return to the original shape when force is applied then removed. So in something that's plastic, you add force to it and it will stay in that shape. Something that has elastic property, you add force to it and you remove the force, it snaps back into its original shape. Another thing I need you to understand is there are different phases in the solid phase. There's multiple solid phases. For instance, when water freezes, it freezes at 32 degrees Celsius, 32 degrees Fahrenheit, 0 degrees Celsius. When water freezes, it forms a hexagonal structure. And also, by the way, this is why water becomes one of the few things that becomes less dense as it becomes a solid. It actually expands into this shape here. But it actually goes through another solid phase change when water gets below 150 degrees Fahrenheit. This doesn't happen very often that we're exposed to, but the shape of water actually changes when it gets colder than that. So from negative 350 degrees Fahrenheit to negative 330 degrees Fahrenheit, water, when it's in the solid form, will create a cubic structure. So there are different phases in solids. And by the way, with water, there's not much of a noticeable difference between these two phases. The densities are almost the same as well. But it does change shape. So the final thing we're going to talk about with engineering materials is shape memory alloys, which is abbreviated SMA, a shape memory alloy. These were discovered by accident in 1962. What happened, there was a board meeting and a sample was bent out of shape many times. So during the board meeting, they're playing with the sample and they're bending it and they're talking. And Dr. Muzi held his lighter underneath the alloy to see what would happen. So they're just in the meeting. He just wants to see what would happen if you heat up this metal. And to everyone's surprise, the metal moved back to its original shape. So when he added heat to it, it moved on its own and it moved back into the shape it was at the beginning of the meeting. In 2014, the Corvette was the first vehicle to incorporate shape memory alloys as actuators as a lighter and more efficient alternative to the hatchback motor. So 2014 Corvettes, their trunk actually has shape memory alloys in there. My point being, where I put these dates in here, is that shape memory alloy is a new material, and we're starting to see it being incorporated more and more right now. Shape memory alloys are alloys that have both plastic and elastic properties. So they can be pushed into new shape without breaking, and they can also return to their new shape. This is very, very unusual. Most things have one but not the other. They take the new shape when bent, but return to the original shape when heated. And that's important to note. So you can bend it, which would be plastic, and then it snaps back to original shape, which is elastic, but this happens when it is heated. They have multiple solid phases. Martensite is the phase we have at low temperatures. So we have this phase, just like water had two phases, we've got two different phases for shape memory alloys. When it's low temperature, it's in the martensite phase, and when it's at high temperatures, it's in the austenite phase. So it shifts back and forth at the different temperatures. If we're going to set a shape memory alloy, this wire right here is the shape memory alloy. And we got this wire on this piece of metal, and there's screws in there holding it into this shape. So we hold it in position, and then we take that and we're going to heat it up. And as we heat it up, it will shift into the austenite phase. This sets the memory of the shape of this wire. Once we take it out and it cools, it will go back into the martensite phase. So the martensite phase is when it's cool, and the austenite phase is when it's hot. And so we take it out and it's set, and the molecules go back into this martensite phase. When it's cooled and it's in its original shape, the martensite shape, it's kind of like these rhomboid structures. I believe that's the name of it, rhomboid. Rhombulus. I'm going to double check that. Yes, I just checked. This is a rhombus. That means the four sides, they have the same distance on the four sides. So we've got this rhombus, and this zigzag shape here, we call this the twined martensite structure, this twined structure here. If we take it and bend up the wire, in the areas that it's bent, we call this the detwined martensite structure. And the is still rhombus, but now instead of being zigzag, it's detwined. They're going to be in rows here. This happens when it's cool and we're physically bending it out of shape. So in some areas here, it'll be in this situation. But it has to have physical force applied to this. This is not a phase change. This is just shifting the rhombus structure, the martensite. If we put it back in water or something warm, we have hot water here, even though it was bent out of shape, it will go back into the austenite structure, and it will go back to the original shape it was cast in the oven. So as we heat it up, it returns to its original shape, and I think it's worth seeing. So we've got a video here from MIT 12 videos, put this together of what I was just talking to you guys about. So let's take a look at this as we end our presentation. So we're heating it up, and we're in the austenite phase right now. We heat it up and we're setting it. He cools it down and it goes into the twined martensite phase. Now it's nice and cool, and taking this shape memory alloy and bending it around, remember, it's not a physical it's a physical change, but it's not a phase change. We're moving it into the detwined martensite stage. So it's getting detwined right here. And I think the really most interesting thing about this is right here. It's detwined. We put it in some hot water and bam, it turns back into austenite. I think that's really cool, and you can take it out. It will go back into the twined the twined martensite, and then you can move it around again. Anyways, I hope you got something from this. If you have any questions, please contact me and let me know. I'd like you guys to make sure you understand this stuff before you get assessed on it. So take care, and I'll talk to you soon. Bye.